Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 36, part A. We are in section 4.2 in the book, and this is correlation. This is the second video on correlation, so this is part 2. Last time we talked about these properties of covariance, which are very important for you to know. And so the covariance of x with y is the same as the covariance of y with x. The order doesn't matter. The covariance of a variable with itself is the variance of that variable. So that tells you that the covariance is a more general or larger or more encompassing concept than just the variance. The variance is a special case of this. The covariance of a random variable with a constant is 0. And then we've given you some answers for the covariance of some combinations of random variables and even a linear combination. And then this last one is very important. You'll want to know this at the tip of your fingertips or the tip of your tongue. You want to be able to know that the variance of x plus y is the variance of x plus the variance of y plus 2 times the covariance of x with y. Okay. We started on the properties of correlation, so I will... the correlation coefficient. This is, rho is the population correlation coefficient. I want to make sure that that is clear. You may have studied the sample correlation coefficient, which is little r. This is the population version. All right, so the properties are that rho of xy is equal to rho of yx. The correlation of a negative with a positive is the negative of the correlation of those variables. And we proved last time that the absolute value of the correlation between two linear combinations of a random variable is simply the correlation of x with y. So the scale, which is the a and the c, and the translation, so b and d, whether it's addition or subtraction, doesn't affect the correlation. So that's a nice property to have, that it's invariant with respect to scale and translation. So this time we're going to start with proving that the correlation coefficient is between -1 and +1, and I've taken this proof from a book called by Casella and Berger, and it's pages 172 to 173 of the second edition. So we're going to consider this function of t, and we're going to set that equal to the expectation of a linear combination of these the differences of the mean from it, or a random variable from its mean here, x and y. And then we're squaring this. That's very important because this makes the expectation positive. So the expectation of a positive value is a positive value. The expectation of a negative value is a negative value. So, so the expectation doesn't change the sign of anything. All right, so we're going to take this linear combination of t and its differences, and we're going to actually square them and expand them. And so we get t squared x minus mu quantity squared, 2t times the two differences, and then the difference of y and mu of y quantity squared. And so when we take the expectation here, remember it's a linear operator, and so we're distributing e, and so I can pull the constant. See, we're taking the expectation with respect to, not with respect to t, okay, but with respect to the random variables here. And so we get e of x minus mu x squared, that's a variance of x, plus 2t, another constant, e of x minus mu x, y minus mu y, and that's the covariance of x and y, plus the expected value of y minus mu y quantity squared, that's a variance of y. And so this is the equation we end up with, and this is going to be greater than or equal to 0 for all t, all real numbers t, because it's the expected value of a non-negative random variable. You may not be able to see it from this expression, but remember that this is just another expression for this, which is, and maybe I should use a different color. So here, this is a positive number. As I said, it can be 0 or positive. Because of the square, it can never be negative. So that means that this quantity can never be negative either. Okay. Now, what we're going to do is we're going to solve for the roots of t. And so we use the quadratic formula, and we have that here. You can step through that if you need to pause the video. And for a real root, we know that the discriminant here, the part under the square root, has to be greater than or equal to 0. And so we can divide, we can factor out 4, or we can cancel. When we add this to both sides of the inequality, we end up with a 4 here and a 4 here, and the constants you can cancel. You can't cancel random variables across equality or inequality without losing a solution. So you don't do that, but constants you can do. All right. So then this also implies that when we take the square root of both sides of this, remember that the square root of let's see, so the absolute value of x is equal to the square root of x squared. So when we take the square root of both sides here, we end up with the absolute value of sigma xy, the covariance. And so the covariance can be negative or positive. So when we take away the absolute value, we use the property of absolute values. We take the negative up to the positive. Remember that these quantities are both positive. The standard deviations are both positive of x and y. Okay, and so now we're going to take, and since we have the same thing on both the top and the bottom of the inequality, we divide by the positive of this. So that value, all sides, all three parts of the inequality. And we end up with this expression, and we have a negative 1 here and a positive 1 here, and this expression in the middle is the definition of rho, and thus we have proved that rho is between negative 1 and positive 1. Now, we want to look at the next property is that we have the, if the absolute value of rho is equal to 1, that is true if and only if there exists some numbers a and b that's not equal to 0, it can be negative, such that the probability that y is equal to a plus bx, that probability that y is equal to that is 1. So in other words, when rho is equal to 1, we have the assurance that there is a linear relationship between x and y. Linear relationship between, sorry, can't hardly read that myself, between x and y, okay? So when rho, the absolute value of rho is 1, when there's a perfect correlation, there has to exist a linear relationship between y and x here. That probability is equal to 1, that it's true, okay? So we're going to also state that if rho is equal to 1, then b, the slope, is greater than 0. And if rho is equal to negative 1, then b is negative. So the slope and the correlation coefficient have the same sign. So I'm going to go over the proof, and we can see that from 4 above, this property 4 up here, that's proof, that the absolute value of rho is 1 if and only if this quantity here is equal to 0. Where did I get that? That's from the discriminant, because if this quantity here is 0 under the discriminant, then square root of 0 is 0, and I'm left with negative 2 sigma x y over 2 sigma x squared, which is the negative sigma x y, which is the covariance, over the variance of x. And so I've put that here. That implies that if rho is equal to 1, then we have this. And that implies that these quantities are equal. And so, of course, this is equal, but I've shown you how that's true up here. All right. And something else that's true is that when rho, the absolute value of rho, is equal to 1, then h of t, our original function up here that we started with, let's clear this out a little bit. So we can see, so this, whoops, so this expression here, that doesn't work very well, does it? I haven't tried the highlighting before. So this expression here, h, has one real root when rho is equal to 1, right? Because this is 0, so that only leaves one possible root, which is this. Okay, let's see if I can find where I was. All right, so it has a single root, t, equal to this, which of course is equal to negative sigma xy over sigma x squared, or the variance of x. Okay, so since this quantity, because it's squared, has to be greater than or equal to 0, the expected value of h of t is equal to 0 only if, you've got it, the probability that this quantity is equal to 0. So if the probability that this quantity is equal to 0 is 1, that's the requirement for us to have h of t equal to 0. And this is if and only if, so it goes both ways. If the probability that this quantity is equal to 0, if that probability is equal to 1, then h of t is equal to 0. And you'll notice that we can take the square root, because we're dealing with positive values here. If we take the square root of this, then, and I don't know what just happened here. Let's see. So something seems to have messed up in my document here. All right, so, all right, that's better. Good. Now, we can take the square root of this, and of course the square root of 0 is 0. And if we take the square root of this, since this quantity here was 0, the square root of it still has to be 0. Okay, the square root of 0 is 0. So we can use that property of the square root to say that that this quantity here is equal to 0, that linear combination. And we can rewrite this by just distributing t across, and then rearranging. We can solve for y. Y is equal to negative tx plus mu y plus mu of x. And again, that probability is still equal to 1. We've just rearranged it. And we can now substitute in y is equal to a plus bx, and we're letting b equal negative t. And we saw that this is true when t, or t was equal to the negative of this, and so the negative of t will be the positive quantity. And again, so we're going to let t be the slope, so negative t equals the slope b, and then this quantity here, we're going to set that as the intercept, and that's going to be a, and so we have mu y plus mu xt, and then we can substitute in for t. Remember that t is going to be, if I take this here for negative t and I make t positive, then this has to become negative here. Okay? So that's what we've done. We substitute in, and we have this equation. And so this is an equation of the line. And you'll notice that b equals negative t has the same sign as rho, which proves our last two statements that says if rho is 1, b is greater than 0. If rho is negative 1, b is less than 0. All right. So I hope that's clear to you. Now, what we have here is we have the expressions for a and b, and you need to know what those are. I've put a box around this, but I also want to put a box around this. These are two different ways that you can write it. If you know rho, you can use sigma y over sigma x. If you don't, if you have just the covariance, it's a covariance over the variance of x squared. And so one mistake here, this should be a capital Y hat equals a plus bx. That is how we write the regression line, okay? Y hat, okay? And I'm sorry, that's from a sample. Yes, I had it right the first time, but I made a mistake. This is not Y hat, this is Y, okay? So no hat here for that. Now, so A, just to make sure that you have this, A is equal to mu y, horrible mu y minus B mu x. So you need to write that down, and you need to have the expression of B. I would have both of these. Okay, so a reality check. If x and y are independent, that should mean that the correlation of x and y is 0. Why? So if x and y are independent, then E of xy is equal to, because x and y are independent, this is the only time this is true, then E of x times y is equal to E of x times E of y. And if you look at the definition of the covariance of xy, it's equal to EXY minus EX times EY. So if these two are equal, then this is equal to 0. And if that's equal to 0, remember that the correlation is sigma xy, or the covariance over sigma x, sigma y. That's going to be 0 as well if this is 0. Okay. So now, the problem with this is that a 0, if x and y are independent, then the correlation between x and y is 0. But if the correlation is 0, you cannot say that x and y are independent. There is a special case with the normal distribution. I don't know of any other. There may be some other distributions, but the normal distribution is the one that we know that's true. But in general, correlation of 0 does not mean that the variables are independent. Okay? However, independent variables have a correlation of 0. Now, if the rho is different from 0, or the absolute value is greater than 0, then x and y are dependent. Okay. So I want to go over some things that confuse students, and that is, one thing is, how do we write E of xy? How do we get this expression? What can we use to solve for E of x times y? Well, if you have the covariance and you have the means, remember that the covariance of x and y equals E of xy minus E of x, E of y, or the means of x, means of y, right? And so you solve that for this expression, and you get the covariance of xy plus the E of x times E of y. Or, if we have the correlation, remember that the correlation, rho, is equal to the covariance divided by the standard deviation of x and the standard deviation of y. Solve for this by multiplying both sides by the denominator, and you can end up with this. Okay? And if you have this is the covariance. Now you can plug in, so this whole quantity is the covariance. Plug that in for the covariance here in the equation that we solved up in number 1, and you have that expression. So you have this expression for E, the expected value of E times x. Or you can use the definition, which should be the last resort. If it's discrete, then we use the summations. If it's continuous, we're going to use the integrals. All right. So I want you to take a look at example 4.2-1 in the textbook. This page may be off because that was a different edition, but I want you to look at 4.2-1, that example. That's your reading assignment. Okay, so please don't forget to scan in your lecture notes and upload them to the Google Drive folder shared with you before midnight of the date listed on the course calendar. You'll want to update your formula sheets for what you've seen today. If you have any questions, come to virtual office hours. If you can't do that, then, of course, please email me. I'm glad to help you, but I'll need 2 things from you. I need a picture of your work so I can see what your thought process is, and I need a picture of the problem so I know what problem we're working on, because I don't have them memorized, contrary to popular belief. All right, I hope you will take care of yourself and stay safe, and we will hope to see you next time.